Rahim, Assalamu alaikum. Welcome to Technically Explained. In the previous video, we discussed the construction of the junction field effect transistor. We said that the major portion of the structure is the N-type material, and drain and the source terminal are connected to this N-type material. We also said that the two P-type materials are connected together and connected to the gate terminal. We say that we have two PN junctions, and because of two PN junctions we have two depletion regions. Now in this video we are going to discuss the working of the junction field effect transistor, that is the working of the JFET. I have divided the working of the JFET in two cases. Case number 1 is the VGS. The voltage between gate to source is equal to 0 volt, and in case number 2 VGS is some negative value, which means that VGS is less than 0 volt. So this is my two cases, and for both the cases we will have the VDS, which is the voltage between drain and source, to be some positive value. So these are my two cases for explaining the working of the junction field effect transistor, and in this video I am going to discuss the case number 1, which is the VGS is equal to 0 volt and VDS is equal to some positive value. So to get VGS is equal to 0 volt, this means that the gate and the source are at the same potential. That is, the potential difference between the gate and source is equal to 0. So to get the same potential for gate and source, what I am going to do is that I am going to connect the gate and source terminal together. Now the gate and source terminal are connected together, and I can assign positive negative over here. And because VGS is equal to 0, so what I am going to do is that I am going to add the ground here, because ground is at 0 volt. So now the condition of VGS has been fulfilled. The next thing is that VDS is equal to some positive value. Let's suppose that VDS is equal to VDD, which is, and this VDD is some positive value. So what I am going to do is that VDS is the potential difference between the drain terminal and the source terminal. So I am going to connect a battery between the drain terminal and the source terminal, and this battery is going to be a positive battery. So now we have a VDD over here, and this VDD is some positive battery, because the positive terminal is connected to the drain and the negative terminal of the battery is connected to the source. Now the current ID is going to flow like this, and this is my conventional current. We know that we have two types of current. One is the conventional current and the other is the electronic current. The conventional current flows in opposite direction to the electronic current. The conventional current flows, the direction of conventional current is the same as the direction of positive charges or holes, where the electronic current is the direction of electrons. Now what we are going to have is that we are going to have electrons flowing over here. Why? Because we have connected a positive here, so the electrons are going to be attracted towards this positive terminal, because electrons are negative charge. So the direction of the electronic flow will be in this direction, and the direction of the conventional current will be in this direction. So electrons are going to flow in this direction, and the conventional current is going to flow, ID is going to flow in this direction. The second thing that we want to talk about is the depletion region. The depletion region is going to become wider as we move to the top here. As we know that we have two depletion regions, and as we move to the top, the depletion region is going to become wider as compared to the bottom. As you can have a look, the depletion region is becoming wider here and here also as compared to the bottom. And the reason for this wide depletion region is that we know that N-type channel provides obstruction to the flow of electrons. So this N-type of channel is is a resistor. Now I can divide this channel into 4 equal resistances. For example, I divide this channel into 4 equal resistances. Fine. This is my drain terminal, this is my source terminal, and we can have a look. The source terminal is connected to the ground, so we have a 0 volt over here, and we have a voltage VDD over here. Let's suppose VDD is equal to 2 volt. So I can have 2 volt over here. Now let's suppose the resistances are uniformly distributed. So I have R over here, R over here, R over here, and R over here, where R is some resistance value and its unit is ohms. Now what will happen is that at this junction I have 2 volt, and in this junction I am going to have 1.5 volt. The reason is that across every resistance I have a potential difference of 0.5 volt. So across this resistance I have a potential difference of 0.5 volt, and then again between these two resistances I have again 0.5 volt. So between ground and this point I have 1 volt, and then again between these two resistances I have 0.5 volt. So between ground and this point I have 1.5 volt, and then again I have 0.5 volt over here, and between ground and this point I have 2 volt. Now if we can have a look, so we have a voltage of say 1.5 volt over here and of 0.5 volt over here. And if you look at the biasing of this, the VGS is connected, this P type is connected to gate which is at 0 volt, but this N type material is connected to some positive value. So this is reverse bias because this N type is connected to some positive value, and we know that when N type is connected to the positive terminal of the battery, we have the reverse bias condition. So now this PN junction here at the upper portion is reverse biased by about 1.5 volt, and this PN junction here is reverse biased by about 0.5 volt. Now we know from the diode discussion that the reverse biased voltage increases the width of the depletion region. So more the diode is reverse biased, the wider is the depletion region. Now here the diode is reverse biased by 1.5 volt, so the depletion region will be wider here as compared to here which is reverse biased by 0.5 volt. So that is why as we move upward, the reverse bias voltage keeps on increasing as demonstrated here. We have 0.5 volt at this point A, we have 1 volt at this point B, and we have 1.5 volt at this point C. So that is why the reverse bias voltage is increasing as we move upward. And because greater the reverse bias voltage, the wider is the depletion region. That is why the depletion region is wider at the top as compared to the bottom. So this was all about the working of the JFET. In the next video, we will explain the characteristics of the junction field effect transistor. Thank you.